Okay, so in this game, EJG works as an equilibrium. So this is, here is beta. It works as an equilibrium even with a belief system mu that specifies 2/3 weight on this and 1/3 weight on this, history having happened if this information set is reached, because this information set is never reached with a positive probability if all players play according to this equilibrium. So the way we formulate our consistency requirement is such that the belief system, there are restrictions on the belief system only for those information sets that are actually reached with a positive probability. So here, player 2 is free to believe whatever she wants in terms of the belief system. Any belief that makes our equilibrium works is okay here, simply because this information set is never actually reached with positive probability. For all information sets that are reached with positive probability, the belief system is restricted, and it's restricted in this way. The probability that you reach H star within I, so the probability of a particular history having occurred within that information set. So for instance, in this information set, for example, that could be the probability of having a history of C. That probability should equal the probability of that H star given beta conditional on, divided by the sum of all histories in II having occurred with that same likelihood. Okay, so what this means is the likelihood of H star occurring given a strategy that is beta, and what this means is that you add up all of the other H's in II, again having occurred with some strategy beta. So let's just do an example. Let's say that the probabilities with which P1 plays C, D, and E are P, Q, and R, and P, Q, and R would have to add up to 1. Then the probability of C having occurred given that you're an information set II would be equal to P, which is the probability of player 1 playing C, divided by P, which is for one of the histories in this information set, plus Q, which is for D. So basically the exercise is Bayes' rule, and the idea is that as player 2, I know that either C or D have occurred. Based off of beta, I know that P1 plays C with the probability P and D with the probability Q. Therefore, if it's C or D, then the likelihood of C is going to be that ratio. And it's as simple as that. Let's look at a few other examples. Remember the Barkov-Stravinsky game? So I'm going to erase this for now. In the Barkov-Stravinsky game, player 1 chooses between B and S, and then player 2 doesn't know what's happened, and player 2 also chooses between B and S, between B and S. Let's say this is 2, 1, 0, 0, 0, 0, 1, 2. Okay, this is the structure of the Barkov-Stravinsky game. In this game, in order to keep player 2 indifferent between playing either B or S, player 1 has to play S with a probability 1/3, B with a probability 2/3, and so for player 2's beliefs to be consistent at this information set, player 2 should think that B has occurred with a 2/3 probability and S has occurred with a 1/3 probability. So here it's very direct because there's only one thing. I mean, here player 1 has only two choices, and the probability distribution over those two choices will determine exactly what beliefs player 2 has to have in equilibrium. But basically in equilibrium, the beliefs have to be consistent with the strategies. Let's do another example. The card game that we discussed earlier. So there you had chance, deciding with a 50-50% chance that 50% probability that the card is either black or red. Here player 1 can either see or raise. And player 2 only observes that player 1 has raised, but doesn't know whether player 1 has a red card or a black card. And so player 2's beliefs should be able to tell player 2 which of these histories has occurred that's leading player 2 to this point. At this point, player 2 can either call or fold. And so here, again, player 2's beliefs have to be consistent with what the actions that player 1 is taking. So if player 1 plays raise with a probability equal to, let's say, PH, when player 1 has a PP, when player 1 has the black card, and PR, when player 1 has a red card, then the likelihood that the card is black, so the likelihood of this history having happened when player 2 is in this information set, is going to be simply PB divided by PB plus PR. Another way of thinking about this is this history, right, could have occurred with the likelihood 1/2 of PB, right? Because you need a 50% chance for the card to be black, and PB is the likelihood that player 1 will choose raise after seeing the black card. So this history occurs with a chance of 1/2 PB. This history occurs with a chance of 1/2 PR. If you know that one of these two histories has occurred because you're in this information set, then the likelihood of this one having happened is going to be 1/2 PB divided by 1/2 PB plus 1/2 PR. Right? The likelihood of this history having happened divided by all of the ways that you could end up in this information set, just adding up the probabilities of all of those histories that could lead you to the same information set. That's the notion of consistency of beliefs that we're going to work with here. Okay, see you in the next video.